Okay, so in this problem we have a step-on tube with acetone and methanol in the liquid phase, and then it goes up to the top where it has a screen on it, and over that screen air is flowing at a high velocity. So as in this problem, acetone is component 1, methanol is referred to as component 2, and air is referred to as component 3. We also declare that the interface of the liquid is Z equals 0, and the top of the step-in tube is Z equals to delta. So some given parameters that we have in this problem are at the surface, the mole fraction of acetone is 0.319, the mole fraction of methanol is 0.528, and the mole fraction of air is 1 minus the sum of those two components. We're also given that the delta is 0.24 meters, the temperature is 325.5 Kelvin, and the pressure in this tube is 99.4 kilopascals. Now we're looking for the molar fluxes of acetone and methanol as they diffuse from 0 to delta. So we're given some more. We're given the Stefan-Maxwell diffusion coefficients for between components 1 and 2, 1 and 3, and 2 and 3, and those are in terms of millimeters squared per second. So, like I said, we're trying to solve for the molar fluxes of acetone and methanol, and since we're given the Stefan-Maxwell diffusion coefficients, we can start by listing out the Stefan-Maxwell relations equations with respect to components 1 and components 2. So starting with component 1, which is acetone, we can say that the change in mole fraction of acetone with respect to the change in distance from 0 to delta is equal to the mole fraction of 1 times the molar flux of 2 minus mole fraction of 2 molar flux of 1 over the concentration times that Stefan-Maxwell diffusion coefficient between components 1 and 2, plus the mole fraction of 1 times the molar flux of 3 minus the mole fraction of 3 times the molar flux of 1. And again, that's over the concentration times, and this time it's the Stefan-Maxwell diffusion coefficient between components 1 and 3. And we can do the same thing for component 2, methanol. We can say the change in the mole fraction of methanol with respect to Z is equal to the mole fraction, in this case it'd be 2 first, mole fraction of 2 times the molar flux of 1 minus the mole flux of 1 times the mole fraction of 1 times the molar flux of 2 over the concentration times the Stefan-Maxwell diffusion coefficient between components 1 and 2. You can say 2 and 1, 1 and 2, they're reversible. It'll be the same Stefan-Maxwell diffusion coefficient. And then again, you add mole fraction of 2 times the molar flux of 3 minus the mole fraction of 3 times the molar flux of 2 all over concentration times Stefan-Maxwell diffusion coefficient between component 2 and 3. So these are the Stefan-Maxwell Stefan-Maxwell relation equations, in regards to components 1 and 2. And as you can see, there are differential equations, and we're looking to solve for the molar fluxes N1 and N2. And in this case, since they're differential equations, we can, considering we have initial values for mole fractions at the surface, we can use a solver to determine the molar fluxes of N1 and N2 in regards to this Stefan tube. However, in order to use that ordinary differential equation solver initial value problem, we need to make initial guesses for the molar flux of 1 and the molar flux of 2. However, one problem with giving just any random number is that if you do that, your solution, your values may never converge and your solution will not be accurate. So not only do we need to make a guess for the molar fluxes of N1 and N2, they need to be close in terms of their order of magnitude, so that our solutions converge, our values converge, and we get the correct solutions. One thing I forgot to mention here is that the molar flux of 3, I haven't been talking about that because the molar flux of 3 here actually goes to 0 in these equations because air is not coming down into the Stefan tube and diffusing into the liquid. So the molar flux of 3 in this case goes to 0 both times in these equations. So now we need to do an order of magnitude estimate in order to determine what order of magnitude we need to use in our, we need to find an order of magnitude estimate for molar fluxes N1 and N2, so that when we do try to use the ordinary differential equation solver with the initial values, we get a solution that converges. So in order to do that, we first need to start by scaling our z value. So we need to create a new term, and that is going to be eta. So it's kind of like a weird n looking thing, and we're going to define eta as z over delta. So by defining eta as z over delta, we're doing two things. We're scaling the variable z, and by doing so, we're essentially right now z is any value between 0 and 0.24 meters, and that's kind of a headache. So one thing to do to make it a little bit easier is to get that variable between 0 and 1. And by doing that, we can take z over the total distance in delta. So any distance z in this tube over the total distance will get you a number between 0 and 1 and tells you how far up the tube that you are. So now that we have eta described, we need to get eta into this equation for into the Stefan-Maxwell relation equations. So we can do that by saying let me move this somewhere else. So that can happen when you don't have a professional setup like myself. All right, moving on. Eta is equal to z over delta. Just try not to have that happen. So we can say that dy. So I can say the change in the constant, the change in mole fraction 1 with respect to z is the same as saying the change in the mole fraction of 1 over with respect to change in eta times the change in eta with respect to z. So these are equivalent. Now, by saying those are equivalent, we know that eta is z over delta. So if we replace eta with z over delta there, we end up with 1 over delta times this change in mole fraction of 1 times a change with respect to eta is equal to this change in mole fraction of 1 with respect to z. So then we can plug in this for this right here, which is what we're going for. Okay, so then by plugging this into that, we can multiply. It'll be this right here on the left side of the equation is equal to this, and then we can multiply by delta and get delta into both these equations right here. So I'm going to erase this, and I can put it down right here by saying, again, we're multiplying delta to both sides to get rid of it on the left side and adding it to both terms on the right side. So instead of dy1 over dz is now dy1 over d eta is equal to, and then again, like I said, delta is being multiplied by both of these. And then this equation remains the same. Mole fraction of 1 times the molar flux of 2 minus the mole fraction of 2 times the molar flux of 1 over the concentration times the Stefan-Maxwell diffusion coefficient between 1 and 2. And then, considering this goes to 0 here, we can now pull out a minus. This minus comes out front now. And we can say the mole fraction of 3 times the molar flux of 1 over the concentration times the Stefan-Maxwell diffusion coefficient between 1 and 3. And I am forgetting that delta goes there as well. So let's actually do that. There we go. Okay. So now that we have eta in this equation and delta over here, we can now make an order of magnitude guess for what we believe the molar flux of 1 and the molar flux of 2 are going to be. So just by looking at pure numbers here, mole fraction of 1 is always going to be between 0 and 1 because mole fractions have to be between 0 and 1. And now that we scaled eta to be z over delta, we know that that also has to be between 0 and 1. Therefore, the change in mole fraction of 1 over with respect to eta is going to be an order of magnitude 1. So the left side of this equation has right like that. An order of magnitude 1 is that notation. A big O. Let's make that even bigger. So this left side will be an order of magnitude of 1. So in order for these to be equivalent, this right side of the equation also needs to be an order of magnitude 1. So we know by looking at values that delta is between 0 and or delta is 0.24, so that's between 0 and 1. Mole fractions of 1 and 2 will be between 0 and 1. And the same for mole fraction of 3. Actually, we can rewrite the mole fraction of 3 to be 1 minus the sum of the other two components. So we got rid of the molar flux of 3 as well as the molar flux and the mole fraction of 3. So now we only have mole fractions of 1 and 2 and the molar flux of 1 and 2. So now we know, back to the order of magnitude estimate, we know that delta is order of magnitude 1. Mole fractions, like I said, have to be between 0 and 1, so the order of magnitude is also 1. And so essentially we need, since these are already going to be on the top is order of magnitude 1, we need to know, and we're trying to guess what the order of magnitude of the mole fluxes are going to be. We need to look at the bottom because when you look at fractions, in order to get an order of magnitude of 1, you need the order of magnitude on the bottom to be equivalent to the order of magnitude on the top, so that when they're divided, they get 1. So whatever the bottom is, the top must be the same thing in order to get an order of magnitude of 1. So when we look at the bottom, we have concentration times the Stefan-Maxwell diffusion coefficients. So if we break these apart, we know that the concentration, so this is not equal to anything else. The concentration is equal to the pressure over the ideal gas constant times temperature. So this replaces concentration in this equation, and we say P over RT times Stefan-Maxwell diffusion coefficient is on the bottom. So when we plug in just raw numbers here, we know that the pressure is let's do another arrow here. The pressure is 10 to the 5th in terms of pascals. And that's from the given parameter. And on the bottom we have the ideal gas constant, and that's around 8. That's 10 to the 5th, not 105. There we go. So we know that's an order of magnitude of around 10, and the temperature is around 300. So 8 times 300 is 2400. So that's around order of magnitude of 1,000, or 10 to the third. So now that we have 10 to the 5th over 10 to the third, we also need to remember that the Stefan-Maxwell diffusion coefficient for gases is 10 to the negative 5th. So on the bottom of this equations, we will have the concentration times the Stefan-Maxwell diffusion coefficients is equal to roughly, these will cancel out, and we're left with 1 over 10 to the third, or 10 to the negative third. So if we have 10 to the negative third on the bottom of these Stefan-Maxwell relation equations, we know that the molar fluxes will also need to be 10 to the negative third, because when you get 10 to the negative third times, again, these are just order of magnitude 1, so you have 10 to the negative third minus a 10 to the negative third number, you get 10 to the negative third on top, you get 10 to the negative third on the bottom, you get equal to 1. 10 over negative 3 over 10 over negative 3, or 10 to the negative third over 10 to the negative third gives you 1. And we know that it must be equal to 1 because the order of magnitude of the change in the mole fraction of 1 with respect to eta is order of magnitude 1. So therefore, when we go to solve the initial value problem in Python, the order of magnitude guesses, the initial guesses for our molar fluxes need to be 10 to the negative third.